All right, I think maybe we can get started. All right, hi everyone. Welcome back to the AMD seminar series. We are very happy to have you with us. We are also delighted to have Nikhil Agarwal as our speaker today. Nikhil is an associate professor of economics at MIT, and he studies the design of markets that match suppliers with consumers without using prices. He has applied his work to markets in education and healthcare settings, including organ donations, residency matching, and school choice. His research is funded by NIH and NSF, and he's also a recipient of the Sloan Research Fellowship. Today, he's going to tell us about choices and outcomes in assignment mechanisms, the allocation of deceased kidney donors. Nikhil, we are very happy to have you with us. Thank you again for joining us today, and the floor is yours.
Thank you very much. I appreciate the invitation. It's a pleasure to be here, and I'm looking forward very much to your comments and questions. So please feel free to interrupt as things come along. This paper is joint work.
Sorry, Nikhil. Just sorry to interrupt you. I just wanted that you reminded me to make this announcement one more time that we want to keep the seminar interactive. So if you have any question during the talk, feel free to raise your hand. We can enable speaking. And of course, at the end of the talk, we have our usual live Q&A as well. All right, sorry.
Great, thanks, Rita. So this paper is joint work with Charles Hodgson at Yale and Paolo Samani at Stanford GSP and NBR. And in this paper, we're going to be thinking about assignment mechanisms, in particular, the allocation of deceased donor kidneys. And we'll be thinking about outcomes and how they're related to choices that agents make in this setup. So as you know, non-price mechanisms are used to allocate a number of scarce goods. And we have mechanisms that elicit preferences of agents, combine them with some priority rules and an assignment mechanism that decides who gets what. An example that you might be familiar with is public school choice or public housing, also deceased donor organs. The market design literature here focuses usually on several notions of what makes a mechanism good, but one of the central notions in this literature is a decision theoretic notion of efficiency. So are agents getting objects that they prefer more? But if you talk to policymakers in this space, they will often focus on other objectives. So school choice, the superintendent of the school might care more about educational achievement than matching students to the schools that they like the most. In the case of deceased donor organs that we'll be thinking about today, healthcare costs and life years from transplantation are focal outcomes. So life year from transplantation is defined as the median number of life years that you would live with a transplant minus the median number of life years you'd be expected to live without a transplant. So it's the number of life years gained from a given transplant, okay? And so the policymakers want to maximize that, not necessarily preferences. And so in this paper, we will propose a way to evaluate a mechanism on the basis of the outcomes that it produces. And we'll think about how you can go about doing that. And one of the things that's going to come through is that when we think about these outcomes, you have to think about how choices interact with the mechanism in order to select who gets what. So which patients get what kind of transplants. And in this particular empirical context, we will think about how we can increase the life years from transplantation by understanding the math between the types of agents and the types of objects that they are assigned to. Okay, and we'll think about what are the consequences of that for the types of mechanisms that should be designed, as well as distributional consequences. Okay, so to give you a little bit of background on the allocation of deceased donor kidneys, let me tell you a few things about how the process works and what the consequences are of a transplantation. So a transplant improves the quality and length of life. It's expected to increase the length of life by about 7-8 years, according to best estimates so far, and saves about $270,000 per transplant, because otherwise these patients are being taken care of on dialysis, which costs the government about $100,000 a year. A transplant is relatively cheap. It's $140,000 one time with very few costs afterwards. And Medicare spends about 7% of its budget, or 1% of the federal budget, is spent on taking care of patients with kidney failure. So it's a big, important problem. Right now, there are about 100,000 patients who are waiting on the list, and in a year, we only transplant about 1/6 of them, and many others are dying while they're waiting for a kidney. Okay, so when someone dies and becomes an organ donor, the person's organs are offered to patients on this waiting list in a priority order, and agents often decline their offers. So the median organ is declined by about 40 patients before it is accepted and transplanted. And the reason why these patients are declining these objects is because if you decline an organ, maybe in a week, in 2 weeks, a month, you might get a different organ that you might prefer more. And so what we want to do is to match patients to organs that is going to improve their outcomes, LYFT being the one that we'll focus on today. Now, I want to pause here and think about whether or not choices are going to be aligned with maximizing lift. There are several reasons why it might not be the case that choices are aligned with lift, even though each agent should benefit, each patient should benefit from an organ that has higher LYFT. First, there might be some agency problems between the patient and the surgeon. The surgeon and the transplant center has some considerations regarding, reimbursement eligibility, et cetera, that might create some tension between what the surgeon wants to do or the transplant center wants to do and what's best for the patient. But even if there aren't any agency problems, there might be incorrect beliefs about which organs are the best suited organs for a given patient. And even if the beliefs are not incorrect, there might be coordination failures because this is like a game where many patients are trying to accept an organ that is good for them, but potentially. And there's no reason why the equilibrium of this game is going to result in an outcome that maximizes LYFT. So the map between allowing people to choose to find an allocation that maximizes LYFT is far from trivial. Okay. Of course, there might be reasons why it is aligned with LYFT, because maybe patients have private information about what's good for them or how well they're doing without a transplant. And so that might be one reason at least. And there might be others that might result in choices being positively aligned with maximizing LYFT. So in this paper, we're going to develop an outcomes-based approach for evaluating assignments, and we'll apply it to this particular context. And the challenge here that we need to solve is that the priorities in the system, the choices that patients make, and the allocations rules themselves will create selection into who gets a transplant and what kinds of transplants they're going to get. Okay, and these specific reasons for selection may create biases that would confound observational studies. So if you look at a patient who received a transplant and an otherwise identical patient based on your data who did not receive a transplant, there are some reasons why these two patients have different outcomes. These reasons could be their choices or perhaps who's lived longer versus not. And so this is going to create some selection into who gets assigned. And we want to purge this selection when we think about evaluating alternative assignments. So the proposed solution here is going to be based on a large literature on ROI selection, which jointly models the choices that people make and their outcomes. Okay, and we're going to estimate this model that's going to have a choice model and a model determining survival outcomes using two complementary sources of quasi-experimental variation. So we're going to try to create experiment-like conditions in estimating this model. Okay, even though there won't be a explicit randomization, we will use some of the tools from the treatment effect literature to think about as if random assignment. So in the analysis of this paper, we will talk about the identification and estimation of LYFT. In this talk, I'm going to be relatively high level and brief about these aspects, these technical aspects. And then we're going to use those methods that are developed in that part of the paper to compare mechanisms with alternative benchmarks and think about the role of choice in this setup. Okay, so just to give you a preview of results, the current allocation system for kidneys generates just under 9 years of LYFT. So a given transplant for a specific patient, on average, increases life by about 9 years. Observational studies are a little bit biased by about 0.6 years. Okay, and the current mechanism is doing better than a random allocation. So if you randomly allocated patients to donors without considering the choices or anything, or the mechanism or anything like that, you'd get about 8 years of LYFT. So there's a gap of about 1 year per patient, which is a large gap. Okay, we will find that there's positive selection into LYFT via the mechanism for several reasons. First of all, the system transplants patients that have high baseline survival and high LYFT. Okay, so patients who are expected to live longer are also, we're going to find the ones who are going to benefit most from the transplant. Now, this is a waiting list in which your priority goes up as time goes on, and so you're going to select people who have high survival just by waiting, and so they're going to end up having higher LYFT. We're also going to find that patients who have a high LYFT from a particular offer are more likely to accept that offer. So that's going to result in some selection because the choices, seeing the choices might be good in trying to get patients the kidneys that are best suited for them. And so these sources of selection are resulting in some gap between observational studies and our estimates, and that could have consequences for the types of assignments that you would recommend. Now, in particular, what we find is that even though the system produces about 9 years of LYFT, there is scope for increasing LYFT further. So if you were an oracle and you knew all of the characteristics of the patients and the donors and et cetera, you could have increased LYFT by another 5 years, okay, which is a huge increase. Okay, but there's a problem that you're going to confront if you want to do this. We're going to find that maximizing LYFT in this setup is going to require you to transplant the healthiest patients. So the healthiest without a transplant. Okay, so the people who would have lived the longest without a transplant would also be the ones who you would recommend a transplant to. So that creates a dilemma because there might be a moral imperative to take care of patients who are sick and might die soon without a transplant. And so these moral issues and this tension comes to the forefront when you start thinking about the outcomes that are generated by the various mechanisms.
Okay. So Nikhil, can I ask one question
yes,
on the previous slide? So when we are about computing this lift, does this include the percentage of kidneys that get discarded? Because there, as you said, many kidneys get rejected, and at some point they get discarded.
Yeah. So Vahide is referring to the fact that about 20% of kidneys that are considered suitable for donation are discarded. In these calculations, I'm going to hold the set of kidneys that are transplanted fixed. Okay. But what we could do is to say that, okay, if a kidney was discarded, can we learn about something about the lift? Now, we don't see an outcome for those kidneys, and they're observationally different. So you'd have to find a way of extrapolating from observationally similar kidneys. But you might worry that they got discarded, which might be indicative of somewhat poor quality in a way that is not quite captured by the observables. So we don't go there. But it may be possible to extend this framework to think about some kind of variation that affects whether a kidney is discarded or not. For example, there's a weekend effect, apparently, where kidneys that are recovered during the weekend are more likely to get discarded. And you might think that that's not related to the quality of the kidney. And so if you can potentially use those types of variation in this framework to think about discards. We aren't doing that in this paper, though, however.
Great. So this 5 extra years is even without including those kidneys.
Yeah. So this is with just reallocating the kidneys to a different set of patients. Okay.
Great. Thanks.
Great. So we're going to draw on a number of different literatures. We're going to rely very heavily on the literatures on estimating treatment effects. This literature is interested in finding as good as experimental conditions in the real world and using that to estimate the effects on outcomes, okay? Even though we do not, without doing a randomized control trial. And so in particular, we will be closely related to the estimation of value-added or ROI-like models. And we'll be extending some of the recent insights in that have taken other data from assignment mechanisms, namely school choice, to learn about treatment effects. Now, the design of the deceased donor kidney allocation system has been really well studied. In operations research, there are many papers by Su, Zenios, and others, Junjun Zhang, Dmitry Butsimas et al., on thinking about how to allocate kidneys to different types of patients. This literature largely takes either a utilitarian approach to evaluation or thinks about the total number of kidneys transplanted. Okay, this is including some of my work, that recent work in economics. And there's a small literature on the counterfactual evaluation of assignment mechanisms as well, in particularly school choice, in static school choice systems, that also takes a utilitarian approach. So our differentiating point is to think about the outcomes very carefully when thinking about alternative assignment rules. Okay. So in the rest of the talk, I'm going to go through the allocation of deceased donors' kidneys a little bit more, talk about the model, how the model is identified and estimated, and then get into the results. Okay. If you have any questions at this point, I'm happy to take them. Okay, great. So let's talk about the kidney allocation system. So as I've briefly mentioned, once an organ becomes available, it is offered in priority order. First, a patient with a perfect tissue type match with that organ is prioritized. So this is as if you have your twins kidney. So given COVID, and we know everything about antibodies and antigens, etc. So imagine that there's a kidney for which your immune system is not going to react. That's a perfect tissue type match. Okay, and so that's a great one to have, because your immune system is not going to attack it, and so it's going to live longer. If you don't have such a kidney, then what's going to happen is that over time your immune response is going to attack the kidney, and so you have to be immunosuppressed. Now, once these perfect tissue type matches are quite rare, once these patients are offered, the allocation systems proceed geographically. First, patients in the local area are offered the kidney. Then if people in that local area say no, then we move on to the regional area, say like the Northeast of the United States. And if then everybody in the Northeast says no, then we go to the national region. And if everybody says no in that region, then the kidney gets discarded. Okay. Now, within each group, each geographical group, there are points for how long you waited, and some characteristics that prioritize pediatric patients for tissue type similarity, etc. But it's predominantly first come, first serve. Like it's first come, first serve with some wrinkles. Okay. So once you offer these patients the kidney, the highest priority patients who accept the offer are the ones who receive the transplant. And this data has been used in observational studies to estimate LYFT. So there's a big heterogeneity across age. So 11 years for older, for young adults, and 7 years for about age 50 plus is what the current estimates are. Okay, and these observational studies are not using as a random variation. So we're going to take data from 2000 to 2010. We have information on every offer that was made for every kidney, the decisions that were made, whether transplant occurred or not. And then we know detailed information about the donor's characteristics. We know rich information about the patient characteristics and characteristics that are specific to the patient and the donor. And we can track patient survival up to the end of 2015. Okay, so we can track up to 15 years of survival data. So what do these survival data allow you to do? So in this picture, I'm showing you two sets of survival curves. The red lines are survival without a transplant, and the blue lines are survival with a transplant. So let's just focus on the red lines for a second. In the left panel, I've got young patients who are below the median age of about 53. And the median young patient without a transplant who has not received a transplant is observed to live about 7 years. So you can see the horizontal dashed line, which is the 50% line, intersecting at about 7 years. Okay. Older patients are expected to live not as long without a transplant, just over 5 years. Okay. Now, with a transplant, the blue lines show you that survival prospects are much better. So the transplanted patients are living much longer. The light blue lines are for donors who both of their kidneys were transplanted. Okay. The darker blue line is for a donor for whom one kidney was discarded and one kidney was transplanted. Okay. And so a kidney gets discarded when people say no, right? And so the blue line is consisting of donors that are not as desirable. Okay. And so the survival curve is a little bit lower. Okay. So a few things to keep in mind here. First, patient heterogeneity is important. Older patients have the prognosis for older patients is worse than prognosis for younger patients. Second, transplantation is correlated with higher survival. Okay, the patients who are transplanted may be different from the patients who are not transplanted, and so you cannot infer causal effects here right away, because what you would like to know is what would happen to a patient who did not get a transplant, but had you transplanted them. And that we'll never see in the data, because you can only see a patient either if they're transplanted or if they're not transplanted. Okay. Third, the choices seem to be potentially correlated with outcomes. The darker blue line is below the light blue line. So that is indicative of choice being important. And finally, if you look at the blue vertical lines, that's waiting time. So the waiting time is about 2.5 years or so, 2.5 years. Okay. And the waiting time is lower for a kidney that had some discard, which makes sense because those kidneys are not as desirable. Okay. So what we're going to try to do in this paper is to get causal analogs of this, to try and purge this of selection bias from various sources that we've discussed already. Okay. So this is where our model comes in. So we're going to have a transplant-specific potential outcomes framework, if you're familiar with the potential outcomes framework. So what we observe for a patient is how long they live, and this value could be potentially censored. So yi is how long a patient lives, patient I lives, and you observe yij if patient I was transplanted with kidney J, in which case Tij is equal to 1. If patient I was not transplanted at all, we'll observe yi0, which is the outcome without any transplant. Okay. So how do these transplants come about? So let's focus on patient I. Imagine this patient got an offer for kidney 1, and this patient said 0. Di1 was 0. So the patient said no. Well, in a little bit, the patient is going to get another offer. Maybe Di2 is also 0. And after a little while, the patient says, yes, Di3 is 1. And then Ti3 is 1. So we see the transplanted outcome for patient I after the third offer was made. There was a fourth potential offer for this patient, but this patient never saw it. And so we'll never see the outcome for that patient for that fourth potential offer. Okay. So our goal is to infer the distributions of yij and yi0 by observing only yi. Okay. And so we're going to assume that there are some latent outcomes that we may or may not observe. And these outcomes are as follows. yi0, which is your outcome without your survival outcome without a transplant, is a function g0 of some observable characteristic of the patient xi and a patient frailty, nu y0. Okay. The outcome with a transplant, yij, depends not only on the patient characteristics xi, but it also depends on the quality of the kidney qj. So the qj is a vector of characteristics of the kidney that are observed. Okay. Then there's nu I1, which is patient frailty with a transplant. So a patient may either do well with a transplant or without a transplant, and nu I0 and nu I1 capture those. And then there's epsilon ij, which is something that affects a match quality between the patient and the donor in the transplant outcome. Okay. Now this model is generated from a hazards model, and you can just write it this way. You can write the survival times in this particular way. Okay. The key assumption here is that there is no unobserved time-varying frailty. So nu I0 and nu I1 do not have a time index that is potentially correlated with other things. Okay. So given these outcomes, we'll also have a model of how agents make decisions. We're going to assume that they are offered objects sequentially, which is as is done in this particular waitlist, and they must either accept or reject an offer. Dij is a binary variable that indicates whether or not the patient accepted an offer. It depends on patient observable characteristics xi. It depends on the quality of the kidney QJ. It depends on nu-ID, which is a patient selectivity term that may be correlated with nu-I0 and nu-I1. And epsilon IJD, which is the match-specific shock that may be correlated with epsilon I1. Okay. Now, this is a binary choice that the agent is making at every single step. But you can microfound it, as I've done in a previous paper, that as an optimal stopping rule. So over time, you get offers, and you compare the value of accepting that offer to the value of waiting. The value of waiting takes into account the fact that you have potential future offers that might come in. And so you compare the value function V to the perceived value of a kidney, and you compare those two. Now, there's one thing called ZI, which is something that's in the decision model, but is not in the outcomes model. Okay, that is going to be a instrument that affects decisions, but not affect outcome. We'll assume that that variable is an instrument in the sense that it's independent of the unobservables in the model. So everything that's Greek is unobservable, everything that's Roman is observable. Okay, so it's going to be Z is going to be independent of nu I, epsilon, etc., and is going to serve as an instrument. What that instrument is going to be clear very soon. But it's something that affects choices, but should not affect, conditional on your choice, the outcome that you get. So imagine that for some reason, because you're in an area that has high or low scarcity of kidneys, you make different decisions. But should you get a particular kidney, it shouldn't affect your outcome. Okay. Now in this model, we're going to allow for rich correlations between the various terms nu and correlations between epsilon ij1 and epsilon ijD. And that's going to result in selection on various margins. So there'll be selection to treatment on yi0. So patients who are not transplanted will be different from patients who are transplanted on how long they would have lived without a transplant. There'll be selection on the average value of a transplant as well. So y bar, which is the average across all kidneys, will also be selected. Patients who potentially are transplanted could live longer without a transplant as opposed to other patients. And there could be selection on match-specific value, yij minus yi bar. And the selection occurs due to a number of reasons. For example, the mechanism creates selection. It has these priority points. It also prioritizes waiting times, so that affects selection due to mortality. And choices will create selection as well. Okay, and so we're going to try to purge this selection. So how are we going to go about doing this? Yes,
Thank you. Quick question. So, so there is this TIJ which says that did this patient get a transplant or not? But does it matter when that happens, right? So yes. Maybe you're talking about 10 years in year 4.
Absolutely,
this patient.
Yeah. I should have mentioned this, so thank you for pointing this out. So time to transplant will be important. And the way you can think about trying to transplant being incorporated into this model is that QJ is a characteristic of the kidney that we observe, XI is a characteristic of the patient that we observe. So we observe the date on which the patient arrived, and we observe the date on which the kidney arrived, and taking the difference between those two, you can get the time to transplant. And so we'll allow for the time to transplant effects.
Great,
okay,
thanks.
But yeah, I should have mentioned that. Great, so let's talk about identification estimation. So we're going to use 2 sources of variation in order to identify our model. The first thing is going to be that we'll assume that offers are independent of the unobservables in the model, conditional on the patient characteristics that we are controlling for. So just because of the luck of the draw, I might get an offer that is different from your offer, okay? Because I potentially signed up today, you signed up a week later, and so we're going to get different sets of offers, okay? And so because we're going to get different sets of offers, we're going to get different transplants, even if we would have made the same decisions. Okay, so that's one source of variation that will allow us to take identical patients, but see them under different types of transplants. Okay, it's as if random. And all of the variation there is coming because of this kind of timing that I just mentioned. The second one is that there'll be a choice shifter ZI that's excluding from outcomes. So imagine that I'm in a region in which kidneys are very scarce. If kidneys are very scarce in my region, I'm going to be less selective than you are. Okay, because I know that I'll have to wait very long before I get the next offer. So I'm going to make different decisions from you. And as a result, my outcomes my transplanted outcome is going to be different. But had I been in your region and received the kidney that you did, my outcome should have been the same. Okay. Now we're going to allow for region fixed effect. So we're going to look at idiosyncratic variation within a region over time, as opposed to across region, because across regions the transplant centers may also be different. Okay. And so we're going to use both sorts of variation to identify the model. And let me give you a brief outline of the proof strategy that we use to show that the distribution of outcomes is identified. So for simplicity, assume that all kidneys in patients are observationally equivalent. And nu-D is the term that affects the selectivity of the patient. It's unobserved. And let's say it's uniformly distributed, okay, for the sake of illustration. Okay. So you have the density, which is the flat line, the flat red line. Now imagine that there are some patients who get one offer and some patients who get no offer, for simplicity. Okay. And there's some patients who accept the first offer and the other set of patients who don't. Okay. Now, the ones who accept the first offer are going to be different from the ones who don't accept the first offer, right? So in particular, people who accept the first offer are less likely to be, are going to be less selective in general. Okay, so the pink line tells you the remaining density of people who have accepted the first offer. So by comparing the outcomes of people who accepted the first offer versus people who got, did not get a transplant, you can get the treatment effect for people who accept the first offer. Now notice that they're different from the average patient, right? Because they're less selective patients. Okay, and so you get a specific effect. That contrast gives you a specific effect between people who get and people who don't get the offer. Okay, now you can do the same thing for people who get two offers versus one offer, and you'll get a different sliver between the pink line and the orange line. Okay, and so on for the various sets of offers. Now, while we can get these contrasts using these offers, we cannot say anything about what would happen under alternative assignment mechanism. In an alternative assignment mechanism, the distribution of selectivity of patients who get transplanted will be different. Okay, and so they may not be described by any of these regions here. So another way to think about this is that if you drew a vertical line anywhere on this graph, so you fix selectivity and you try to think about what are the transplantation effects for people of a given selectivity, this type of variation will be useless at telling you anything about that. Okay. So here's where our second instrument comes in, which is a choice shifter. This is going to be something that is to affect the choices that people make, but not the outcome given the transplant that they get. Okay. And we're going to use variation in beliefs about kidney availability in order to think of this choice shifter. So we will think about the past offers and donors that were made to a patient who had the same blood type, signed up in the same region as me, okay? But the offers that were made in the past year to patients of that type, okay? And so if the past is predictive of the future, then these patients might make different decisions in response to this measure of scarcity, and therefore might end up with different transplants. Okay, and so this instrument needs to satisfy two types of requirements. The first is what's called an exclusion restriction. Specifically, the past donors and offers should not affect the outcomes except through the kidney that I finally get. Okay, so that seems natural. If I expect something different and therefore I'm deciding to decline a kidney, it should not affect what would have happened to me had I been transplanted that kidney. Okay. The second one is relevance. It should affect which kidney that I was assigned to. If it doesn't affect which kidney I'm assigned to, it has no power in distinguishing between those two things. Okay. And so the data shows, in fact, that it is true that these past donors and past offers is correlated with decisions. Here's a bin scatter plot that shows you that. So if you look in the horizontal axis as the log of 1 plus the number of donors, that were offered in the past year to patients with the same blood type in the same region as me, and correlate that with the acceptance rate of patients under various conditions of that form, taking into account fixed effects for the time, which is the year, and fixed effects for the region, then you see this downward trend. So if scarcity is high, so there are few donors that were offered in the past, acceptance rates are high. All right. And in the paper, we go through balance and observables to show that this instrument is not correlated with other confounding things that could be correlated with patient quality. So why is this type of variation useful? So let's go back to the picture that I showed you a few slides ago. And what I've got here now are two additional lines, the dashed lines, which didn't exist earlier. So the other colored lines are the same as before. Now there are two more dashed lines. These dashed lines are comparing regions that have high scarcity. Low scarcity. Okay, low scarcity versus the solid lines of high scarcity. Now you can see that what this choice shifter does is that it shifts the marginal patient who gets the kidney. It shifts the selectivity type of the marginal patients who get the kidney. And this shift is useful because it tells us about the effects on people who are in a different group, okay? Namely that little sliver between the dashed line and the solid line. Now, this is not yet a proof, but in the paper, we go through how this kind of variation, when combined with the offer variation, can be used to learn about exactly what I had said earlier. That if you drew a vertical line through one of these points here, you can tell about the treatment effects for that specific selectivity type. And the proof is based on deconvolution-like methods. Okay, so it's a little bit involved, but that's sort of how it sort of works. Okay, so the theorems specifically combine this instrument about scarcity with the offer instrument to disambiguate the effects of match-specific effects from the selectivity effects. Okay, now when we go about estimating the model, we use a relatively simple specification. We parameterize the survival curve and the choice equation using a linearized version. So we take the survival quantities, capital YI and capital YIJ, use a box-Cox transformation, and then specify it as a linear normal specification. So we assume that the error terms nu I, nu 1, and nu d are jointly normal, and the epsilon terms are also jointly normal. The decision model is like a probit model. Okay, so it's a binary choice model that looks like a probit model, which is consistent with the dynamic decision model that you would have wanted to write down. Okay, so we'll estimate this model using a Gibbs sampler, which is equivalent to maximum likelihood. So it's a Bayesian technique that in a large sample produces estimates that are asymptotically equivalent to the maximum likelihood estimator. Okay.
Nikhil, can I ask a question about the instrument?
Mm-hmm.
So the past donor and past, was it organ quality that you were using? What was the?
We're going to use alternatively past donors or past number of offers.
Past number of offers, great. So how is it? So the relevance condition shows that my choice is affected by the past donors and past number of offers that I have seen. And so how, I'm trying to understand how I reconcile this with the assumption that the news, the unobservables are not time dependent. Is that
okay? So first of all, it's a past number of offers or past number of donors to a comparison group that are similar to you, not you.
I see. Not my past. Not
so I'm excluding you, and I'm looking at people who registered 1 year before you. And in the last year, what did they get?
I see.
That's the prediction. So I'm excluding you. And so it's a little bit different from the issue that you're interested in, which is the time varying unobservables. There is one unobservable in a model that is time varying, which is epsilon ij, which is because every kidney arrives at a different time. And so there's going to be a shock that is kidney specific. So there'll be some time varying shocks there. Okay, does that help answer the question?
Yeah, so you're saying that this new is, so the unobservable, right? So the unobservable that we're assuming that does not evolve over time is only patient dependent. Is that right?
Yeah, so in the decision model, there are two unobservables, nu ID and epsilon IJD. Nu ID is not time varying. Now, the reason why we can't make it time varying, we would love to make it time varying, is that we only observe one yes for any patient, because once you say yes, you get the transplant and you're done. And similarly, we only observe one outcome for a patient, which is like once you get a transplant or you don't get a transplant, you see one survival outcome. So since we don't have repeated measurements, it's hard to include time varying unobservables.
Right. Right. Can I think of similar arguments that look at comparison groups? So patients that look similar to me on the observables.
Right.
And think of whether that gives me information about the distribution of the new eyes that could be varying over time.
I'm not sure how you would do that. I'm happy to talk about it offline.
Yeah, we can talk about this
we
offline.
weren't able to. I mean, there's a large literature in this space that suggests that it might be difficult to do that. So I'm not entirely sure how to do that, but I'd love suggestions if you have any. Okay, so great. So let's get into the results that come from this this approach. So first, let's look at the life years from transplantation in the system. So we're going to first look at the difference between the median life years with and without a transplant. And as I mentioned earlier, the observational estimates give you about 8 years of life, and our estimates give you a little bit higher, 8.6 years of life. And one of the things that you see is that whether you use past donors or past offers or future donors, the estimates are very similar. Okay, but instrumenting matters. Okay, the untransplanted survival of patients that received a transplant is higher than patients who did not receive a transplant. So there's some selection into transplantation that's based on mortality. Given waiting time as being important, that is understandable. Okay. Vahide, are we going to? I have about 5 minutes left. Is that right?
So we have until 2 p.m., but we want to hopefully keep a few minutes for Q&A. But yeah,
okay, great.
No,
so I'm going to try to finish in about 5 minutes. Okay, that way we'll have some time in Q&A. Okay, great. So here's a plot that looks at the untransplanted survival and the average transplanted survival across various patients. And the blue shades tell you where the mass is. And so think about this as density plot, okay, in 3 dimensions. The darker regions have higher density. The straight dashed line is the 45-degree line. And so what you can see is that patients with high untransplanted survival are also the ones who have high transplanted survival from the average transplant, okay? The dots in the middle are the bin means, okay? And you can see that the slope of the dots is higher than the 45-degree line. So the gap between transplanted survival and untransplanted survival is increasing the larger the untransplanted survival is. So patients with high untransplanted survival have high lift, all right? And so in order to increase lift, this suggests that you might have to transplant patients who are healthier on baseline, okay? This graph shows you a bin scatter plot of the acceptance probability versus lift for 2 groups of patients, patients who were transplanted and patients who were not transplanted. So the higher the lift, the more likely you are to say yes, which makes sense because these patients want to increase their, one of the reasons why they want to get a kidney transplant is to increase to extend their life. The transplanted patients tend to be less selective they have a higher acceptance probability than the untransplanted patients, which also is sensible because the fact that they got transplanted means that they probably had higher acceptance rates. Okay, so that's going to results in potential selection due to choice, the kinds of selection that could bias the observational studies before. And so let's put this together and think about the life years from transplantation from the realized transplant against the life years from transplantation against a potential transplant. The straight dashed line is still the 45-degree line, and the dots are bin scatter plots, and the blue lines are a density plot. And you can see that there's a small gap between the dots and the 45-degree line. The dots are slightly below, which means that the lift from the realized transplant is higher than the lift from the potential transplant. So there's some match-specific gains that are being realized, but these are not very big gains. Okay, and the dotted lines are not very far below, and the blue line is very closely clustered against a 45-degree line. Okay, so realized transplants are better than average, but most of the heterogeneity in transplant outcomes is across patients than across donors. So the standard deviation is about 6.6 years across patients, but only 1 year across donors, and about half a year that is match specific. So most of the heterogeneity is across patients than across donors or match specific. So let's put this together to think about the realized assignment and alternatives. The realized assignment in 2005, to each computation, we focused on 2005 for this calculation, yields 8.78 years of life. If you did a random assignment, you'd get only about 7.87 years. So the realized assignment is doing better than random. Okay. Now you might ask, how much of this is coming from choice versus the mechanism? So if you remove choice and you just give kidneys to the highest priority patient on the kidney list, then you would get about 8.01 years. So it's a little bit higher than random assignment, but not much higher. So most of the difference between random assignment and realized assignment is coming from choices. Patients are selecting kidneys, or patients are selecting into transplantation based on their decisions, and those decisions are correlated with good outcomes. Okay. A big part of this is coming from the set of patients that are selected. So if you look at a random assignment amongst the set of patients that are transplanted, you get to 8.23 years, which is about 40% of the gap between random and realized. So selecting patients is important. The remaining gap is selecting which kidneys they get transplanted. Now, what is the theoretical bound on how many life years from transplantation could you get by just retransplanting the donors that were transplanted, the organs that were transplanted, not accounting for potential discards being reduced, as Vahide mentioned in the beginning? Well, you could get at most 13.84 years, okay, of LYFT. Now, that requires you to know a lot of things. You need to know the unobserved frailty, the new terms in our model, okay? And maybe as a planner, you cannot know these, all right? But what you could do is you could take the observables in our model in principle, and you could reassign patients and donors based on just the observables. And that is going to give you 10.48 years, which is a lot relative to the baseline, okay? And if you take 1 year of life multiplied by the value of statistical life year and scale it across this market, you get about $1 billion worth of benefits. Okay, so that's quite a lot based on the best estimates of the value of a statistical life year. But in doing so, a big part of it is coming from, in increasing these gains, a big part of it is coming from selecting which patients are transplanted. If you have severe distributional constraints and you don't want to make sure that any patient who is transplanted does not go transplanted, then you can only get to about 9.5 years. So the potential gain is much smaller. This means that the planner is going to face an interesting dilemma, an important dilemma, between transplanting patients who are going to have their life extended the most by these transplants versus transplanted relatively sick patients who might otherwise die without a transplant. So in column 1, you look at the average patient. Relative to the average patient, the realized patient that is transplanted happens to be younger. You can see that young adults are more likely to be transplanted, and age 60 plus is less likely to be transplanted. Transplanted patients are less likely to be diabetic, and the untransplanted survival is higher. Okay, the optimal assignment the lift maximizing assignment leans on this difference even more, transplanting yet healthier patients. So this results in an equity efficiency trade-off because there may be a moral imperative to transplant the sickest patients who might soon die, and there may be some concerns about discriminating patients with specific characteristics. So I'm ready to conclude now. So in this paper, we proposed using outcomes as a basis for comparing various assignments. This is in line with keeping, this is in line with the policymakers' goals of increasing, for example, LYFT in this setting. And in order to understand the effects of assignments on these outcomes, we needed to use a model that combined the choices with the outcomes that we observe, because choices result in selection. But then you can also use some of the instruments that come from choices, like these choice shifters, that help you identify the relevant quantities of interest. We identified a dilemma between increasing aggregate outcomes and distributional barriers. And I would like to point out that I think that similar issues may be important elsewhere as well. For example, imagine that you have complementarities between good students and high quality schools. So the gains maximizing assignment would have the highest quality students, the best students matched with the highest quality schools. That's going to result in significant inequality that may be problematic. And it may be important to understand the consequences of doing so in order to think about how to advise a school district. So in future research, it'd be interesting to leverage the choice itself to improve outcomes. Here we've compared alternative assignments, and explicitly to include these distributional constraints in thinking about which assignments may make a lot of sense. So that's it, and we have a little bit of time for questions.
Yeah, thank you so much, Nikhil, for this very interesting talk. I have some questions, but I'm gonna first let audience ask their questions. So if you have any question, feel free to raise your hand. All right, maybe I get started and then we can continue with other questions. So that's very, very interesting. One question I had was that you are fixing the mechanism here, right? So the allocation mechanism is not changing. And you identify this interesting dilemma. Is there a way that at least part of this tension can be alleviated through changing that allocation mechanism? Is there a room for other mechanism design maybe?
Yeah, so we are looking at alternative assignments right now. And so what you'd have to do is design mechanisms, I think, that explicitly consider these distributional effects. Mm-hmm. So one of the things that, if you go to the kidney committees, one of the things that they strongly consider is across, different types of race, ethnicity, et cetera, who's getting what kind of transplants. Mm-hmm. And so you'd have to explicitly incorporate those into the design problem. And you have to think about how choices interact with the rules that you use. Because one thing that we've observed in the past is that when the mechanism changes, people's behavior also changes. Yep. So we need to be able to predict that. And I have a previous paper that looks at that. And there are some other people in the OR community like Barishata, et cetera, who have looked at models in which the behavior responds to the change in the mechanism. So what you'd like to do is to propose another rule and then simulate what would happen in the counterfactual world in terms of what choice they would make and what would that result in terms of outcomes. And so that's, I think, a fruitful area for future research.
Right. So it's not the case that there's a fundamental limit and in terms of efficiency versus equity, and then we are kind of close to that limit with the current mechanism.
Yeah, so let me go back to this picture here, okay? So I would say the answer is no to your question because I don't think we are close because, so if you got rid of equity considerations, then you'd get to 13.84 years. Yes. Okay, now if you had the most stringent equity consideration, which is, it's not necessarily the most stringent, but one very stringent consideration is that people who were transplanted in the current mechanism should get a transplant in any other mechanism, then the limit is 9.5 years. Mm-hmm. Okay, so uh, I don't know if that gap makes you feel like it's close or not, but there still is a
No,
gap.
it's not. Yeah, for sure, for sure.
There
Yeah,
still is a gap between the realized assignment and the optimal assignment amongst the set of patients that are already transplanted.
yeah. Great. That's fascinating. All right, awesome. Any other questions? All right. So if not, I want to finish with one more question, which is how much of it is how much of this decision is somehow shared between, let's say, two patients because they have the same doctor? Is that something that you observe in data, or like you think that this is really patient-specific decision?
Yeah, so the doctors are advising patients and making decisions on their behalf, and they may be having cross patient considerations. Now, that creates more of a challenge in predicting what would happen in counterfactual mechanisms rather than counterfactual assignments.
I see.
The reason why it shouldn't affect our calculations so far is that you might worry that cross-patient considerations are important in decisions, but that would show up in our model through this, potentially through this epsilon ij term. Okay? I know we're not explicitly allowing it to be correlated across patients, etc., but that'll be like an idiosyncratic reason why one patient said no and the other patient said yes. Okay.
Got it.
Uh,
I see.
so we are primarily using the decision making aspect to generate some variation in who gets a kidney. Okay. And so it may be not as necessary.
Got it.
But in predicting counterfactual assignments, you may worry more about this issue.
I see.
I see a
Great.
question in the Q&A.
Yes.
Should I go ahead and try to answer that?
Yeah, sure.
Okay, so Shivam Gupta asked, what is the feasible set of assignments in the optimal mechanism? I should have said that more clearly. So we are solving the optimal assignment problem in the in this 13.84 number. So the feasibility constraints are that no organ can be assigned to more than one patient. No patient can be assigned more than one organ. And it must be the case that the patient has arrived before the donor and that the patient did not die before the donor arrived. Okay, so the patient is alive when the donor arrives, and and is registered when the donor arrives. Does that answer the question? Yeah. Okay, great.
Yeah, I think great. All right, perfect. Thank you so much, Nikhil, for this amazing talk. We appreciate it. And thanks to everyone for attending our seminar. I think this concludes our today's seminar. I wish everyone a great weekend.
Thank you very much. Appreciate it.
Sure, of course. All right. Shivam also says, thank you for the great talk. So just want to make sure you saw that.
Great, thanks.
All right.
Can I ask you a question that's
Yes.
just based off of what you were saying about discarding kidneys?
Yeah.
I found that very interesting, that the light blue line and the dark blue line with like the donors who had one of their kidneys discarded, but not the other.
Yeah.
I guess like when people are making their choices, do they know that like the kidney that they're considering, the pair of it has been discarded, or like are those things?
No, they don't know that. The way it works is that you're asked to make decisions, and then if there aren't two accepts, if there's only one accept, then one of the kidneys gets discarded. And so, however, you're more likely to say no if the kidney is of marginal quality. So donors who have one of their kidneys discarded are more likely to be of marginal quality. So that's sort of the thought process behind splitting it up that way.
Thank you.
Good, thanks.
Great. Thank you again. It was great seeing you, Nikhil.
Great seeing you. Thanks
Yeah,
very
thank
much.
you so much.
Thanks.
Yeah.
Bye-bye.
Bye. Bye, everyone.
Thanks for having me.
Sure, of course.